Hello friends. So today we are going to discuss 4 questions, and these 4 questions are from, you can say, the topic is the fields of a moving charges. Okay. So in the first question, one second. Okay. So in the first question it is given that the aluminum sheet A, as shown in the figure, is suspended by an insulating thread between the surfaces uniformly by the bent aluminum sheet B. The sheets A and B are oppositely charged. The difference in the potential is V. This causes a force F in addition to the weight of A, pulling A downward. If we can measure the force F and know the various dimensions, we should be able to infer V. Work out a formula given V in terms of F and other relevant dimensions. So basically we have to find out the value of the force F, we have to find out the potential V, and in terms of specifically the F and other relative parts. So in this question basically, the question is quite lengthy one, but in short form we can say that we are having a sheet A and there is sheet B which is in terms of a marked as a U, and this sheet A is hung by a thread, and sheet A and sheet B are oppositely charged. Okay. So this is the basic question that is given to us, and so in this case we are supposed to find out the potential, and for that we are going to first of all find out the force, and in order to find out the force we should be knowing, we are going to solve it with respect to the energy, because it is much better, because the capacitor is, these are going to behave like a capacitor, two sheets A and B, and so we are going to identify first of all what is the capacitor configuration, and from there we are going to move forward. So we are given that we have to identify the capacitor configuration. Okay. And so in this case, okay, so we are having sheet A and there are two surfaces of the bent sheet B, and we are having two surfaces of bent sheet B. So it means this will be resulting in the formation of a capacitor, or we can say that this will result in the formation of two parallel plate capacitors, and they will be connected in parallel. So this configuration results in two parallel plate capacitors, and these capacitors are in parallel. So let us identify, because in order to find out the capacitance of a parallel plate capacitor, standard formula we already know, that our C is equal to epsilon naught A upon D, where A is the area and the D is the distance between the plates. So first of all, let's identify respectively their distances. So we start with the left gap. And this left gap is our sheet A and left surface of our B. So our left gap is our sheet A plus left surface of sheet B, and let us call this as capacitor 1. And then is our right gap, and this right gap will be our sheet A and the right surface of B, left surface of sheet B. Right surface of sheet B, and let us call this as our C2. Now we come to our area part, because we are going to only interested in the area of overlap. Therefore we can say for each capacitor, we can say our plate area will be equal to B multiplied by our S. Okay. And their separation is our Y. It's our Y. Therefore, let's calculate the value of C1. Our C1, which is our epsilon naught A upon D, and this will be coming as our epsilon naught B multiplied by our S and divided by Y. And our this and our C2 will be also equal to epsilon naught B times S and divided by Y. And so let's calculate the total capacitance. So you can say our total capacitance, that is C is equal to C1 plus C2, and so because C1 and C2 are same, so you can write this as twice of C1, so giving us twice epsilon naught Bs upon Y. And now let's calculate what will be the energy stored. So we can say the stored energy So the stored energy, that is our U, is equal to half CV square, and we substitute value of C, so this comes as our 1 by 2 epsilon naught Bs Y multiplied by V square, and this 2 and 2 cancels out, So we get our U is equal to our epsilon naught Bs V square upon Y. And so if we are going to find, like I said, our force by using the energy method. So it means if the sheet A moves downward by a small distance, then the overlap is also going to increase by that small distance. Therefore, we can say that the force in the downward direction is, let us suppose, our F, and this F will be equal to, suppose it is moving by small distance dx in the downward direction. So you can say our force F will be equal to our du multiplied by divided by our dx, and dx we can say is nothing but our d of s, okay, because here distance is our s. Therefore we can say this is our du by ds. And we already know value of our energy, that is U, and in this case we are having our V, our Y, all are constant. Therefore we only variable is our S, because as the sheet is moving in the downward direction, the overlap, which is denoted as S, is going to change. Rest of dimensions are the same. Therefore the force will be equal to, because here it is S, so this will be ds by ds, which will be equal to 1. So we get the epsilon naught B V square upon Y, and we are supposed to solve it for our potential difference. Okay. Therefore we can write that our potential difference V will be equal to the force multiplied by Y and epsilon naught B and its square root. So this is the value of our potential difference that was required. Next question. So in this question, a nylon filament 0.01 centimeter in diameter and 4 centimeter long, there are 5 into 10⁸ extra electrons distributed uniformly over the surface. What is the electric field strength at the surface of the filament? So we are giving here two parts, and these two parts is nothing but the frame of reference is different. So in part A, it states that in the rest frame of the filament, and part B in a frame in which the filament is moving at a speed of 0.9 c in the direction parallel to its length. Okay. So in both the cases, we are supposed to find out what will be the value of our electric field. Okay. And these type of question in general, these are called as a relativistic electromagnetism. Okay. In general, these type of problems are called as a relativistic electromagnetism. Relativistic. Electromagnetism. And here we are given as a nylon filament, and this nylon filament we are going to treat this as a long uniformly charged cylinder. So we are given that we are having a nylon filament, and this nylon filament we are going to treat it as a long uniformly charged cylinder. And so first of all, we are going to find out what will be the total charge that will be inside this uniform cylinder. Therefore, we can say that the total charge which is suppose our Q, and that will be equal to our number of electrons multiplied by charge on one electron. Number of electrons given to us as a 5 into 10 to the power 8. Charge on one electron is 1.6 into 10 to the power minus 19. So from here we get that the total charge Q is our 8 into 10 to the power minus 11 coulombs. And we are only interested in the magnitude part, because the electron obviously it will be negative. So, but here we are only interested in the magnitude. So let us start with the part A, and part A is our electric field in the rest frame. Part A is our field in rest frame. And for that, we are going to find out the charge per unit length. So we have a charge per unit length. Let us suppose that's our lambda, which will be equal to our total charge divided by total length. And total charge is our 8 into 10 to the power minus 11. And the length is our 4 into 10 to the power minus 12. So from here we get that the value of lambda is our 2 into 10 to the power minus 9 coulomb per meter. So this is our charge per unit length. Next we are going to find out, because like we said, we are going to treat this this filament as a long charge cylinder. Therefore, we can say that the electric field at the surface, electric field at the surface, and which is our E, is equal to our charge per unit length. This is 2 pi epsilon naught and our R. And so we simply substitute the values. We get this value of electric field. Lambda is our 2 into 10 to the power minus 9. So this comes as our 2 pi. And our epsilon naught is our 8.854 into 10 to the power minus 12, and radius is our 5 into 10 to the power minus 5. So this gives us that the value of electric field is approximately equal to 7.2 into 10 to the power minus 5 Newton per coulomb. And this is in the, we can say, field in the rest frame, electric field in the rest frame. Okay. Because rest frame basically means that the electrons are moving, our filament is stationary. Now we are going to find out our filament is moving. So that is our part B. In part B, we can say our field when our filament moves. And under this condition, the relativistic part comes into the picture. A relativistic effect appears. And here it is also given that the motion is parallel to its length. So that is given to us. So we are given that the motion is parallel to its length. And under this condition, if the motion is parallel to its length, one important concept comes into the picture, that is called as a Lorentz contraction. So this results in our Lorentz contraction. And this Lorentz contraction will be resulting in a new length. So we can say our new length, that is our L prime, will be equal to L divided by a factor, that is our gamma. And this gamma is nothing but our relativistic parameter. So this gamma is equal to our 1 upon 1 minus v square divided by c square and its square root. Okay. And here v is the velocity which is given to us as a point over 9 times c. Therefore we can write that our gamma is equal to 1 upon 1 minus, and this comes as our 0.9 c and divided by c whole square and its square root. So this will be 1 minus 0.81 and square root. So value of gamma will be approximately equal to 2.29. Okay. And so we know that the charge is not going to change, but like we said, the length is going to change. Okay, so therefore the linear charge density also going to change. From here we already know that charge is invariant. But the length contracts. Therefore, from here we can write that linear charge density, obviously it is going to increase. So you can say our linear charge density increases. And let us suppose new linear charge density lambda prime, that will be equal to gamma multiplied by the original linear charge density. Okay. And the electric field for this particular case will also going to change. Okay. Therefore we can further write that our electric field of a moving infinite line of a moving infinite line, that is E prime, will be equal to this factor gamma multiplied by the original electric field. Therefore we substitute value of gamma, that is our 2.29, Original electric field we know is our 7.2 into 10 to the power 5. Therefore, we get that the electric field E prime when our wire is moving, filament is moving in this case, is 1.65 into 10 to the power 6 Newton per Coulomb. So we can clearly see that the value of the electric field is going to change when only wire is moving, because of the charge, that is 7.2, and when the filament is moving it changes because of our this contraction. Next question. In this case it is given a charge Q1 is at rest at the origin and a charge Q2 moves with a speed beta times c in the x direction along z is equal to b. For what value of theta shown in the figure will the horizontal component of the force on Q1 be maximum? What is the theta when beta is equal to 1, approximately 1, and when beta is approximately equal to 0? That's their limits. That is quite easy. But for the first part, basic figure is given to us. We are having Q1 at the origin and charge Q2 is at a certain angle theta. Okay. And it is moving with the speed beta times c along the line, and this line is defined by z is equal to b. Okay. And we have to find out the horizontal component and its maximum value of the force. Okay. That we have to find out. And so let us call this distance our r, and this will be obviously our b. Therefore, we can write that our sine of theta will be equal to our b upon r. So from here we can say that our r is equal to b upon sine of theta. And we are going to use the standard formula for electric field of a uniformly moving charge. Electric field of a uniformly moving charge, and at a constant velocity which is given as beta c, and we can say the electric field at an angle of theta, it will be equal to 1 upon 4 pi epsilon naught, and we have the charge which is moving, that is our Q2, 1 minus beta square, and the distance between the two charges, and it comes as 1 minus beta square sine square theta and whole raised to power 3 by 2. So this is the electric field of a uniformly moving charge at angle theta, okay, and this is for two charge system. Okay. And we have to remember that one of the charge is stationary, Q1 is stationary, only Q2 is moving. Okay. Whose velocity is given to us as beta times c. Beta is some vector. Okay. Like in previous question, it was our 0.9. And we already know value of r, so we r substitute back in the question. Okay. Therefore, we can write that our E of theta will be equal to, this comes as 1 upon 4 pi epsilon naught, and r was our b upon sine theta, so this comes as our b square 1 minus beta square sine square theta 3 by 2, and this is a q2 1 minus beta square, and it comes now as a sine square theta. Okay. Now we are interested in the horizontal component of the force. That is our requirement, and we know that the force is nothing but our charge multiplied by the electric field, that we already know. You can say we are given that our q1 charge is at rest. Therefore, we can write the value of the force will be equal to our q1 times our electric field. So it's horizontal component. Horizontal component, we can write that our f of x, horizontal component of the force f of x will be equal to our f cos of theta. F is our q1 times E. So this comes as q1 times E. Now let me write this as E of theta times cos of theta. So we substitute here E of theta. Therefore we get that the horizontal component, that is of fx, will be equal to, this comes as our q1 q2 4 pi epsilon naught and 1 minus beta square sine square theta, and this is our b square 1 minus beta square sine square theta whole raised to over 3 by 2 and cos. So we have to maximize this particular thing. So in this case, we are only mainly interested in this part, because the rest of the things are our constant. So we can denote this as by another variable. Let us solve this as our f of theta, and it comes as our sine square theta cos of theta 1 minus beta square sine square theta, and we have this as our 3 by 2. But in this equation we have two variables, sine as well as cos. So we are going to convert this into our one variable. And for that, we are going to put, let S is equal to sine square theta. Therefore, we can write that our cos of theta will be equal to 1 minus S. Therefore, we get that our f of theta will be equal to our S and square root of 1 minus S and 1 minus beta square times S, and this is our 3 by 2. So we have to maximize this. So it's much better if you maximize its square. Okay. So we can simply square it. So f of square will be equal to our S square 1 minus S divided by our 1 minus beta square S and whole raised to power 3. Okay. So let us denote this by another variable, that is our g of s. So we are going to maximize this g of s, and so obviously for maximization we know we are going to differentiate it and equate it equal to 0. So let me rewrite it as g of s will be equal to our numerator and denominator. Okay. And this numerator is our s square 1 minus s, and our denominator is our, it's denominator is 1 minus beta square s whole raised to power 3. Okay. So let us differentiate it. So we get this as a g of prime will be equal to, this is our denominator square, numerator prime minus numerator as it is, denominator prime. And we are only interested in the denominator part, okay, because we are going to equate equal to 0. So we are only interested in this part, d n prime d minus n d prime, which will be equal to 0. And so let us do our n prime. Our n prime will be equal to our 2s minus 3s square. So our n prime, let me write it here only. So here we get our n prime will be equal to our 2s minus 3s square, and our d prime will be equal to our minus 3 beta square and 1 minus beta square s whole raised to power 2. Now we substitute them back into this particular equation. This is a lengthy solution obviously, and so we get this as our 2s minus 3s square times 1 minus beta s, and this is our cube, minus n as it is, square 1 minus s, and d prime is minus 3 beta square 1 minus beta square s and whole square. So straightforward, I'm going to write the final value of s. Therefore we are going to get the value of s, and this is equal to 0. So value of s will be equal to over 2 and 3 minus beta square, and we know that our s is nothing but our sine square theta. Therefore, for, like we said, for maximization, we can write this as our sine square theta max is equal to 2 upon 3 minus beta square. And now we do the limit part. First is that beta tends to 0. So our beta tends to 0, we get this as a sine of will be equal to our 2 by 3, which is approximately gives that value of theta is our 54.7. And then we have our beta tends to 1. So we get this as our sine square theta will be equal to our 2 divided by 2, giving us our theta is equal to our 90 degree. So this was our condition that our horizontal component of the force will be maximum under this condition, and these two were the limits part. Next question. In this question, it is almost same as the previous one with minor difference. In a laboratory frame, a proton is at rest at the origin at t is equal to 0. At that instant, a negative pion, charge minus E, that has been traveling along x-axis is at a speed of 0.6 c reaches the point x is equal to 0.01 centimeter. There are no other charges around. What is the magnitude of the force on the point pion, and what is the magnitude of force on the proton? So this is the basic question, and here the proton is at rest, so we can just draw, and everything in motion in x direction. Okay, so we are only interested in x-axis. So this is our x-axis, and our proton is at the origin. So this is our proton, which is at x equals 0. and its position is given as ever t is equal to 0. So when the proton is at t is equal to 0, we are having a pion that will be at x is equal to 0.01 centimeter, and there are no other charges present. Okay, so there are two charges only. And so first of all, let's find out what's the magnitude force on the pion. Okay, so the proton is stationary. It is going to apply a force on our, because proton is at rest, so it is going to apply a force on this pion. So the force on our pion. And our proton is at rest. Proton is at rest. Therefore, our electric field will be equal to 1 upon 4 pi epsilon naught, and this comes as E upon R square. Okay, this is our R. And so we substitute the values, we get this as our 8.99 into 10 to the power 9, and charge is our 1.6 into 10 to the power minus 19. R is our 1 into 10 to the power minus 4 whole square. Therefore, we get the value of electric field is equal to 0.144 Newton per Coulomb. And from here we can easily find out our force. So we can say our force will be equal to charge multiplied by the electric field. And let us call this as force on our pin. So this is F pi. F pi is equal to our 1.6 into 10 to the power minus 19, and electric field is our 0.144. So we get the force on this pinion because of the proton is our 2.3 into 10 to the power minus 20 Newton, and its direction obviously will be attractive. Okay, so direction will be towards the proton, so it will be attractive. And now we are going to find out the force on the proton. Now in this case we can clearly understand the difference. Okay, let me write it first of all. In the second part we are going to find out the force on proton. And when we found out the force on pion, our proton was at rest. Now we are going to find out the force on proton, but our charge is moving. Okay, so the formula is going to change. So it means now we are going to use the electric field of a moving charge. Therefore, you can say that electric field of a moving charge . Electric field of a moving charge. And suppose that is given as E, then its formula is standard. We already dealt in this first question. So this will be 1 upon 4 pi epsilon naught. Our charge 1 minus beta square r square 1 minus beta square sine square theta and whole raised to power 3 by 2. And this electric field is for a certain angle theta. Okay, general formula, and according to our requirement we can find out value of theta like we did in first case also. Okay. And this angle theta is with respect to our x-axis. So we know that our motion is along our x-axis. So value of theta in this case will be equal to 0. Because the proton is also lying on x-axis, and this is a proton and this is a pion. It is also both are in along x-axis. So value of theta is equal to 0. Therefore we can say that our sine of theta will be equal to 0. So this solves our this part. We can say our denominator is our, because this terms goes away and this is 1, so only r square is left. Therefore we can say that value of electric field is equal to 1 upon 4 pi epsilon naught charge 1 minus beta square, and this is left with our r square. And value of beta is, it is given as beta times c. Okay, so this is beta, so this is 0.6. Okay, so we can easily solve this. Therefore our, so we can say this is equal to, our charge is our electron, and 1 minus beta square will be our 0.064 times 1 upon 4 pi epsilon naught charge divided by r square. And this is the same formula as our electric field, okay, which we already found out. Therefore we can say that electric field will be equal to then 0.64 times our 0.144, which comes approximately as 0.0922 Newton per coulomb. Now we can find out the force. So we can say the force on proton will be our charge multiplied by the electric field. So this comes as 1.6 into 10 to the power minus 19 and 0.0922. Therefore our force on the proton is equal to 1.48 10 to the power minus 20 Newton, and its direction will be towards the pinion. Direction will be towards a pion, not pinion. So these were the questions for today, and in this case we try to solve how the value of the electric field or the value of force changes, or formula itself changes, when the relativistic formula we are going to, which we are used in this particular case. And we have to remember that the formula for electric field which we used is a general formula, whichever this one. So it can be modified according to our requirement. Okay, so this completes all the questions for today. Thank you.